In this experiment, we are going to find the specific heat capacity of a solid substance. It is the metal lead which we are going to measure the specific heat capacity. And the method we are going to use for that is called method of mixtures. As you can see, method of mixtures involves a heat insulated calorimeter like this. Then we are going to heat up some lead shots, sufficient amount of lead shots, and mix that with water inside the calorimeter. And since the calorimeter is heat insulated, we can assume that the heat supplied by the lead shots is equal to the heat gained by water. Then taking the necessary temperature readings and the mass readings, we can find the specific heat capacity of lead. First, let's consider the materials and apparatus required for the experiment. Obviously, you need the calorimeter, stirrer, and the thermometer. This thermometer is calibrated from 0 to 50 centigrades. Then, to heat up these lead shots, we need this setup. It contains this tube. It is called boiling tube. It is like a test tube, but it can bear higher temperatures. So it is called a boiling tube. Then this vessel is called water heater. Then this thermometer. It is to measure the temperature of water. This thermometer is calibrated from 0 to 100 centigrades. And this is the tripod, Bunsen burner, and there is a wire gas on which the water heater is placed. So that is the experimental setup. And furthermore, there is a heat insulated plate. So the heat coming from the Bunsen burner is prevented by this heat insulated plate. Okay, then let's consider the method to do the experiment step by step. First, you have to measure the mass of empty calorimeter with the stirrer. So let's say that measurement is M1. So this is the mass of empty calorimeter with stirrer. Before heating up the lead shots, we have to take the temperature, the initial temperature of water. Let's say the temperature is θ1. So this should be around the room temperature. Actually, this is the room temperature. That is the temperature of water initially before adding heat to the system. Then you have to fill the calorimeter up to a height 1 centimeter below the brim of the calorimeter. So this height is about 1 centimeter. Then you have to measure the mass of calorimeter with water. Now it is with water. Let's say that measurement is M2. So if we subtract this from these values, that is M2 minus M1, we can find the mass of water contained in the calorimeter, that is M2 minus M1. Then we have to heat up the lead shots. So for that we are going to use this setup. You have to admit lead shots, a sufficient amount of lead shots into the boiling tube and turn on the Bunsen burner. So the water boils. After a while the water boils and you can measure the temperature of water from this thermometer. So you will notice that the temperature is increasing, and at a certain point, once the water starts boiling, this reading becomes steady. So it means the water is at the boiling point. So you will have to record that temperature. Normally it should be around 100 centigrades. So that heat has almost transferred into these lead shots. After a while, we can assume that the temperature of lead shots also is at 100 centigrades. Okay, let's say the temperature value from this thermometer is theta 2. Theta 2. So this is the temperature we take as the initial temperature of lead shots. Typically, this is around 100 centigrades. Then we are going to mix the lead shots with water. So you have to mix the lead shots with water and close down this lid and keep stirring. Then you will notice that the temperature reading of this thermometer keeps rising, and it reaches a maximum value after a while when it starts to drop. Normally this happens quickly because the lead can provide heat to water very quickly, because the lead is a good heat conductor. So you have to take that reading immediately, right? The maximum temperature, that is, let's say that is theta 3. So theta 3 is the maximum temperature of the mixture, theta 3. After that, we can get the mass of this. After that, we can get the mass of the mixture. Once you have added the lead shots, you have to take the mass of this whole thing. It means the calorimeter, lead shots, and the water. Let's say that measurement is M3. So if you subtract this M2 from M3, you can find the mass of lead shots. You can find the mass of lead shots. Remember that M2 is the mass of calorimeter with water, and M3 is mass of calorimeter plus water plus lead shots. So if you subtract these two values, you can get the mass of lead shots. So if I remind you the list of readings, again, this M1 is the mass of empty calorimeter, M2 is the mass of empty calorimeter plus water. This is the initial temperature of water, and this theta 2 is the temperature of lead shots. Theta 3 is the final or the maximum temperature of the mixture after you add lead shots. And then this M3 is the mass of calorimeter, water, and lead shots. So this order is very necessary. You have to get readings according to this order. You should not take the M3 reading before theta 3, because this theta 3 reading comes very quickly and it reaches the maximum temperature, and the temperature starts to drop quickly. So before taking the reading M3, you have to take the temperature readings. So you cannot mix this. The readings should be in order when you are doing the experiment. So additional to these measurements from the experiment, we are going to need two data from a data book. That is, those are CW, that is the specific heat capacity of water. Then CL, that is the specific heat capacity of calorimeter material. So that material can be aluminium or copper. Then let's say C, let's say the specific heat capacity of lead. as C. So this term is what we are going to find. Okay, let's consider how to write an equation involving this all the terms. As I have mentioned before, heat gained by water and the calorimeter. Heat gained by water and the calorimeter should be equal to the heat supplied by lead shorts, assuming that there's no heat loss to the surrounding. So that we can make that assumption because this calorimeter is heat insulated. We are going to express another better way to justify that assumption later, which is called heat compensation method. For now, let's say this is well heat insulated. So we can make this equation, that is heat supplied by lead shorts is equal to heat gained by water plus calorimeter. Okay, let's see how to write this in terms of these terms. First, heat supplied by lead shorts. First, we need to get the mass of lead shorts. So that is M3 minus M2. M2 is the mass of calorimeter with water. This is mass of calorimeter with water plus lead shorts. So from this we can get the mass of lead shorts only. So mass of lead shorts is M3 minus M2. Then we are going to multiply this by the specific heat capacity of lead. This term is what we are going to find in this case. Then the temperature difference for lead shorts. Initially, the temperature of lead was at around 100 centigrades. We took it as theta 2. And this is the initial temperature of lead shorts. And it comes to the final temperature of the system once it reaches the equilibrium. So this is theta 3. That is the final temperature. So this is the temperature difference for lead shorts. Then I'm going to write the expression for heat gained by water plus calorimeter. So this is the mass of water, M2 minus M1. Then I'm going to multiply that by the specific heat capacity of water. And the water initially was at theta 1, finally it is at theta 3. Now the temperature of water has increased, so you have to subtract theta 1 from theta 3. So the temperature difference is theta 3 minus theta 1. So this is for heat gained by water. Then another term, heat gained by calorimeter, let's say plus mass of calorimeter, as we know, that is M1. Then specific heat capacity of calorimeter material, that we took as Cl. Then the temperature difference for calorimeter as well, it is theta 3 minus theta 2. So this term is for the heat gained by the calorimeter. Okay, if we study this equation, all these terms are known. M3 we measured, M2 measured, theta 2, theta 3, those are measured. Then Cl and Cw can be taken from the data book. So all these terms we can calculate. All these terms we can calculate, except for this term, that is the specific heat capacity of lead. So by substituting this and solving the equation, we can find the specific heat capacity of lead. Okay, so that is the experimental procedure you have to follow in order to find the specific heat capacity of lead. There are some special notes when it comes to this experiment. Then let's consider what are those special notes. First, we earlier mentioned that there must be a heat insulated plate between the water heater and the calorimeter. The reason for that is when you are adding like lead and while you are taking measurements, the heat can be transferred via air or radiation here to the calorimeter. So you have to prevent it by putting a heat insulated plate between heater and the calorimeter. Another way you can do this is by placing this heater from a far away distance. You can use those in order to prevent the heat coming from heater to the calorimeter, so it won't cause an error. Another note you have to consider is when you are adding lead shocks into the calorimeter. So you have to open the lid, and when you are adding lead shocks, the water can splashes out. So you have to prevent that. When you are adding it, you have to be careful that the water is not splashing out. Another thing is you have to get lead shocks. You cannot use like a lead cube, large lead cube or lead powder. So if you use lead powder, it can float over the water surface here, and it will provide heat to air in this space. So that could cause an error for the experiment. So you cannot use lead powder, lead as powder. Then you can use a large lead cube for this. It is because if the cube is large, it could take large time, large time in order for the heat to transfer to water. So if it takes a large time, it could cause the errors to increase. So if it takes a large time, we cannot say that the heat loss to the surrounding is negligible. So we have to prevent using a large cube as well. So the proper solution is using lead shocks, that is small lead shocks. Another note you have to consider is that you can use the same experimental setup in order to find the specific heat capacity of a liquid. So let's say you know the specific heat capacity of the solid material which we are going to use here, and you don't know the specific heat capacity of the liquid. So you can solve by substituting and following the same procedure. You can find the specific heat capacity of that liquid. Then I'm going to explain how to use heat compensation method for this experiment. In order to use that, the initial temperature of water should be about 5 centigrades below the room temperature. Let's say the room temperature is at 25 centigrades. So initially you have to take water at about 20 centigrades. So initially we'll have to add some ice in order to gain this temperature. Then you keep adding lead shocks into these, and the temperature starts to rise. The temperature starts to rise, but the temperature of the mixture is below the room temperature. So in this case, the surrounding provides heat into the system. Then further you have to keep adding lead. and the temperature of mixture goes above 25 centigrades. And you have to do this till the temperature of mixture reaches about 30 centigrades. So once the temperature is more than 25 centigrades, the system starts to give out heat from the system. Since the temperature range is same in both cases, we can assume that the heat coming to the system is equal to heat moving away from the system. So you can assume that the heat loss to the surrounding is negligible by the method of compensation. So this is a better method rather than using a heat insulation for the calorimeter. As you can see here, the temperature of mixture has risen by about 10 centigrade, from 20 centigrades to 30 centigrade. But initially we don't know how much of a mass to be added to the calorimeter in order to get that 10 centigrade rise in temperature. So in order to figure out that mass, the mass of lead shots, you have to do a pilot experiment prior to this experiment. So you can figure out the mass of lead shots required to have 10 centigrade of rise in temperature. Okay, that is it for the experiment. If you further need to clarify the concepts behind these experiments, you will have to do structure essay questions and read their clarifications as well.